Obviously the club doesn't have its own antennas for doing things like Jota and the field day, and that's the antennas that we were looking to build were for 20 metres, 15 metres and 10 metres. This design up here is something I come up with the 10 metres, and you saw it actually in there in the photo before that had this idea that John had done. The design parameters for all these antennas, we decided the antenna had to cover basically the whole of the operating bandwidth on 20, 15 or 10 with a 1:1, 1.5 is to 1 SWR or less, and try to get at least 20 dB front to back across the whole band. So the 10 metre one ended up like this. The boom length here is 8 feet long, so it's very short, but the outstanding feature of this particular antenna is the bandwidth. And if we look at the SWR plot, this antenna, by the way, is 50 ohm feed, so there's no need to actually do any matching. We just need to put a 1:1 balun at the feed point, and it matches directly to 50 ohm cable. So if I just put the program through to do a sweep across the operating bandwidth of the antenna, we'll see the SWR curve of it, and it's very, very close to this in the real world. It's surprising how close this is actually. So the left-hand side of the graph is 27 meg, the right-hand side of the graph is 29.7. So where we cross the 1.5 is to 1 point there is at 27.2 megs, and we see the operating bandwidth is extremely wide at, over 2 meg. Okay, so that was the first design parameter we've got from 28 megs, which is here, to 29.7, which is the top end of the FM segment, easily under 1.5 to 1. But along with that as well, it's okay to get the bandwidth, but we try to keep the front to back good across the operating bandwidth as well. So if we look at the actual front to back of the antenna, first of all, this is the frequency. We'll check it out as 28.5 megs. So this is our plot here, and as we can see, this is our front to back. We've got nearly 31 dB, which is extremely good out of the 4-element antenna on an 8-foot boom. At 28 megs, so at the bottom end of our band, we can see there we've still got 22, so we're still better than our 20 dB that we wanted. And up on, if we look at say 29.6 megs, so we're looking at a range now of 1.6 megs. We've still managed to get about 16 dB, so that's, we've met the parameters we wanted to meet. We've got the operating bandwidth with a good SWR across the whole band, so there's no need to tune it for the phone or the CW section. And the other thing is that we just have a look at it actually over real ground. All these antennas have been modelled at 12 metres high over real ground. So when we compare them all, we're comparing apples with apples. So the plot over real ground at 12 metres high, we can see we've got a forward gain of about 12.7 dBi, which is extremely good. So on the 10 metre antenna, it's not obvious when you first look at it how this antenna actually works. And as you saw, we've got a tremendous amount of bandwidth out of the antenna. This antenna, although it's 4-element, this element here isn't actually active on the bottom part of the band, and this element here isn't active on the top half of the band. I'll show you what I mean. If we just take the frequency down to say 28 megs, and we just run it, and then we have a look at the current that's induced into each element. Right, the purple lines on here, I'll just shrink that down again, they represent current. Okay, so what I'll do is I'll blow the current up. We can see that at the moment, element number 2, which is actually the fed element, see he's got the most current out of all of them. So he's doing all the work and he's the actual driven element. As we push the frequency up, so say we take it up to say now 29.5 megs, we'll see something really interesting happen. The element that's actually driven by the feed line, okay, see what's happened now? The one element that's fed, which is element 2, actually has less current in it than element 3. So these two elements are, in actual fact, both driven elements. This element here is what's termed open sleeve couple to this element. So he takes on the function of a second driven element. So as we increase in frequency, the load goes from this guy and transfers over to this guy. So he doesn't do a lot of directivity or front to back in the antenna. He's just there to get our bandwidth. But that's how we've managed to squeeze that much out of the antenna and still keep the front to back good, because we've got basically, you know, two driven elements that are helping us there. What we found happened, but this spacing between these two is only 190 mil or something, isn't it? Okay, so it's only about that far. What we found is when these element tips, as the antenna moves and those element tips move together, obviously they're very tightly coupled, so that impedance changes quite dramatically, and we could see the feed impedance going like this with just the elements moving in the breeze. So what we've done is, at the end of those elements, you saw those like yellow strips that we had across between these two. They're actually strips of circuit board material that we drilled. We etched the copper off, and John inserted a nutsert in the end of this element, so up in the tube, the circuit board screws to that one, and then it's got a hole that slides over the other element. So what that does is just keep that spacing fixed. So if the two elements move, they've got to move together in unison. They can't actually, you know, get closer or further apart. And as soon as we did that, it fixed the problem. So that's just a simple thing we added. It added no weight to the antenna, nothing to the complexity, but it's only because we've got two parasitic elements that are very, very close together in terms of a wavelength, and we could actually see the impedance as the thing just moved, as we shook it. You could just see the impedance changing. So that spacing there is obviously fairly critical, and more to the point, it must be maintained. So, well, yeah, I actually use, if we were to do that commercially, we'd actually use 3.2 mil FR4 fiberglass material, and I get it CNC machined out. And then we get a green solder mask, so it's weather resistant and everything. But in 3.2, those little T-pieces that you've seen that I've made, they're 3.2. You'd never bend one in a million years. That's just what we had on a Sunday afternoon, so it worked. And again, it's only the first one that we've done, and we've got to overcome all these little ideas. But so far, that's matched the model just about, kilohertz for kilohertz, hasn't it?
Yeah.
So, I'm finished now. Can we turn this off, Graham? Or?
Yep.
Uncle Glenn? Oh, yeah.
You want to...